Hello everyone and thanks for watching. This is Fluence's Industrial Wastewater and Biogas Tech Talk. My name is Jason Bowman. I hope you enjoy. Alright, so let's talk about digesters. You have no idea how many people come up to us and say, aren't all digesters the same? Well, in truth, not really. On a global basis, there's at least 10 digester technologies that I'm aware of. Today, we're going to cover a few. All right, so we're here to talk about digesters. Let's jump right in. As I mentioned, there's at least 10 concepts on a global basis that I'm familiar with. Today, we're really going to focus on 3, but I'm going to give you a list of all the options that I'm aware of. So let's start. You have a CSTR process, that's a complete mixed reactor. You have a UASB process. You have recuperative thickening. We're going to talk about that in this presentation. We have granular. We'll also talk about that in this presentation. Then you have linear vortex, you have plug flow, you have lagoon, you have fluidized bed reactors, and the list goes on and on. So why are there so many different styles? Before we can really answer that, we need to focus on the design fundamentals and what it means to design a digester. Most people know the basics about digesters. Today we're going to talk about anaerobic digesters specifically. So an anaerobic digester takes in organic wastes. This can be a solid form, a liquid form, or a slurry, i.e. a combination of that. And what happens in the process is we're relying on bacteria, microorganisms to break down this organic waste into more favorable byproducts. So a few things are happening here. Number one, biomethane is created, so this is a renewable energy source. Number two, the physical waste volume or solids volume is physically reduced. And number three, we're producing an effluent called a digestate that typically has residual nutrients such as nitrogen and phosphorus, which can be used for fertilizer, land application, and several other uses. So let's focus a bit more on the bacteria because it becomes important when we start talking about different feedstocks. So what are the bacteria really doing? Well, number one, they're physically reducing the waste volume. But number two, which is perhaps more critical, is that they're physically changing the molecular structure of the waste or the feedstock coming into the process. So this is important because we need to understand that different influent situations, different feedstocks, different wastes will carry a different molecular structure, a different calorie content, and so on. And the bacteria will behave differently. So let's focus on that. Okay, so we briefly mentioned the word feedstock. Well, what is feedstock? This can be a combination of things. This can be manure, this can be farm byproducts, agricultural byproducts, food and beverage manufacturing, meat processing, the waste from your kitchen. The list goes on and on. Within the US, there are literally 1,000 SIC codes, that's industrial codes for manufacturing practices. Each one of these has a completely different waste and wastewater profile. Not all of these are organic in nature, but it goes to show you that there's a lot of different wastes being generated. So what we're focused on is the composition of this wastewater because it has different calorie content. Different compositions may have different carbon bonds, and these carbon bonds may take longer to break down, they may take less time to break down, or they may be structured in a way that they have a very high calorie content. So this chart here does a pretty good job of explaining the difference between types of wastes, and we've broken it down into 6 categories here, and the degradability time that is required based on the structure of the waste. So this is loosely referred to as biodegradability. So we see here that lipids and fats carry a very, very high energy content. We see that simple sugars take a very short time to break down, whereas complex carbs may take longer to break down. So this is all very important when we start talking about different digester styles because it influences a number of things. Number one, how the bacteria respond. Number two, how much time they need to do it. And number three, how much active bacteria that we need to maintain to ensure that the digester is doing what it's supposed to do. All right, so now we have a good overview of why different feedstocks have different energy composition and molecular structure. A lot of different industries out there, a lot of different feedstocks. So let's turn our attention to the basic design considerations. How are we starting to arrive at the size and the style of digester that's going to fit your specific application? At a high level, there's really 4 things we look for. Number one, organic loading rate. So this is the relative organic mass to digester volume ratio. It basically says how much organic do you have coming in versus how large or how much volume we need to reduce or remove that organic load. So this is going to vary based on the biodegradability and based on the style of digester, and we'll talk about that more in a minute. The second design consideration, which is probably one of the more, let's say, important design considerations, is the solids retention time. Solids retention time, in this case, what we're saying is the bacterial solids or the volatile solids. How long these solids are retained within the reactor, how long do they have to perform the work? So the way solids retention time is measured is the amount of active biomass within the reactor versus how much is being removed or wasted on a daily basis. What you'll find in practice in an operation is that some digesters say plug flow, essentially what comes in is what goes out. Other digesters have a more sophisticated control strategy where these bacterial solids can be collected and recirculated. So in this manner, you can maintain the time that the bacteria have to do the work. And this can be decoupled from the hydraulic retention time. And this becomes really critical when we talk about different digester styles. So the third design consideration, I just mentioned it, hydraulic retention time. This is just a high-level overview of how long the solids or liquid slurry is retained within the reactor. So when we look at design considerations, the solids retention time and the hydraulic retention time in a lot of situations are kind of one and the same. In other situations, again, I mentioned that some digesters have a mechanism to recirculate, to collect and recirculate bacteria. Well, in this manner, we can actually decouple the solids retention time from the hydraulic retention time. This is why some digesters are much more high rate than other digesters. So obviously, we're talking about bacteria, the biodegradability, how long the bacteria have to do their work. Well, you have to make sure the bacteria are happy. So the fourth thing we look at is what is the pH, temperature, nutrient profile. We kind of collectively refer to this as micronutrients and operational parameters. So as long as those parameters are in check, we can make sure the bacteria are happy. We can start to control and manipulate some of the other parameters that we discussed here. So let's get into more detail on that. Now that we have a better understanding of feedstock variability and the basic design considerations, we can finally turn our attention to the different digester styles. So as I mentioned previously, there's at least 10 styles, 10 strategies that I'm aware of on a global basis. Here I'm going to focus on 3 because I feel like these are the most widely used and some of the more stable systems that can be applied across multiple types of feedstocks. So what we're going to focus on here is the conventional CSTR process, a recuperative thickening process, and then a high rate granular process. And we're going to talk about how each of these accept different types of feedstocks and the operational control mechanisms used to make sure that, again, we're keeping that bacteria happy. So let's start our digester journey with a more conventional CSTR process. So this is the most simple, probably the most widely used process on a global basis. These systems typically take in wastes with high percent solids, and that can be anything from manure projects to meat byproducts to post-consumer waste to landfill organic waste diversion. So very flexible type of process, very simple, but it does require a high hydraulic retention time. This is because given the type of waste, given the type of solids that come in, we need sufficient hydrolysis time and we need sufficient time for the bacteria to grow, establish, and break down the matter. As I said, these systems are very simple. This is because they do not operate with an external sludge recirculation. So what comes in is essentially what goes out. In other words, for every gallon that comes into the tank, 1 gallon is going to exit the tank. Again, very simple. This is what's known as a complete mix process, where in theory, every point inside of the tank has the same concentration. The issue here is that we need a high hydraulic retention time because we have to have a high solids retention time. Since there is no external sludge recirculation, the hydraulic retention time and the solids retention time are the same in this case. After the CSTR, there was kind of an evolution on the classical CSTR process. As I mentioned, the CSTR does not have an external sludge recirculation. So the system is very simple, but typically is very, very large. So the next step in evolution for digester design was to utilize what's called an external sludge recirculation. So I mentioned with the CSTR that for every 1 gallon that goes in, 1 gallon goes out. Well, that 1 gallon that's going out carries residual bacteria, residual solids, nutrients, etc. So by capturing this effluent, this digestate, we can actually separate the bacteria mass, the solid mass, and we can return a portion of that back to the digester. So what does this do? Well, it helps us to establish a much higher active biomass within the CSTR process. So we refer to this digester strategy as recuperative thickening. This has the added benefit of decoupling the solids retention time from the hydraulic retention time. In other words, every 1 part of solid that leaves the system, we can actually grab this, collect it, and recirculate it back to the system multiple times, 2, 3, 4, 5 times if we wish. So in this way, the mass of bacteria comes into contact with the waste more often. And we don't have to have as high of an HRT for this to happen. So that's what I mean by the SRT and the HRT being decoupled in this situation. So compared to a conventional CSTR process that may have an organic loading rate of 1, maybe up to 6 kilograms per cubic meter in the best case, the recuperative style can increase that by 50, 60%. So we see organic loading rates on the order of 8, 9, 10 kilograms per cubic meter in some cases. Up to this point, we've really discussed what I would consider low rate and medium rate digesters. Now, those digesters are very simple, very stable when we're talking about the recuperative thickening process, but they're typically geared toward higher percent solids. So these are normally like secondary streams or facilities that the sole purpose is to create a biogas powerhouse. Well, what about other wastewaters that may not have those type of solids but still have a very high concentration of soluble organics? Well, when we're left with high solubility, low solid situations, the bacteria behave a little differently. So in these situations, what we find is anytime there's dissolved sugar, starches, simple carbohydrates, the bacteria like to form in granules. So we can take advantage of this. If we can capture those granules, separate based on density or based on their size, and recirculate a certain density or a certain size, we can actually maintain a very high concentration of active biomass within the digester reactor. So similar to the recuperative thickening process, we're decoupling the solids retention time and the hydraulic retention time. So we're basically recirculating these granules 2, 3, 4 times, however many times we deem necessary to maintain a specific SRT in the system. What you find here is that the way the bacteria develops the solids retention time eventually leads to a very low hydraulic retention time. Now, these systems, again, are more geared toward primary effluents. They're used for pretreatment for industrial sites or even secondary polishing in some situations. So these systems can take COD values up to 30 grams per liter, typically operate with 80 or 90% removal efficiency. And again, this is all achieved in a very low retention time, hydraulic retention time. So these systems typically will have a hydraulic retention time less than 2 days because we're able to maintain such a high concentration of active biomass with the granular recirculation. Until this point in the presentation, we've covered 3 main digester strategies. I want to turn our attention toward the application and commercialization aspects of digesters. There's one stereotype that I would really like to overcome here, and that is that all digesters are built with the same purpose. And that purpose is to have a mega biogas powerhouse. This is not really true. It can be true. It's true in areas where we have a high enough population density or areas where there's a high concentration of agricultural production. And these areas do tend to benefit more from these mega digester projects, but these projects are typically developer driven and the logistics are such that it makes sense. What I would like to note is that more frequently we find these digesters applied on a more decentralized or a more holistic level. So we have smaller systems being applied at the localized industrial level. These digesters can provide a mechanism to treat wastewater or reduce their sludge volumes or change the impact to their carbon footprint. So this approach often affords a more holistic waste treatment or wastewater treatment mechanism and can reduce the burden to downstream areas or receiving bodies of water. Obviously, at the same time, it's producing biogas, but what I want to point out is these systems have a more holistic wastewater reduction footprint and not necessarily need to be a biogas powerhouse. All right, so there we have it, 30,000 foot overview. We've seen that based on different inlet feed conditions that there may be multiple options for treating waste, and we've shown that not all digesters are the same. There's really no one single style of digester that can be applied to all types of wastes. I hope that this information helps to provide a frame of reference and an initial introduction to digester designs. Fluence is always happy to help you with your water and wastewater needs. Thank you, and I hope to see you again on the next Tech Talk.